Okay, so today we'll continue with memory organization. Last hour I explained how we connect the internal units in the memory, main memory. We said that it consists of RS flip-flops, and we can, using select and read-write inputs, we can store something in that cell, and we can read something from that cell. And also I explained associative memory, what type of hardware can be added to that main memory structure so that we can both store data in the main memory and also we can do very fast search operations in the memory by hardware. Now today we'll continue with memory organization and we'll see different types of memory. We'll continue with cache memory actually. So this is the hierarchy of storage units in a computer. We can store data in registers, in main memory, or in some auxiliary devices. Registers are on the chip. You remember accumulator, memory buffer register, they are special purpose registers. But in addition to that, we can store, we can use registers like register 0, register 1, register 2, to a set of registers to store the data, intermediate data. So these are those registers that we can store the data. The registers are inside the CPU, as I said. And as they're inside the CPU, it is very fast to access the registers. So registers are the fastest storage units in a computer. But the problem is their number of registers that you can store in a chip is very limited. You may have 128 registers, 256 registers. You may have a larger set of registers, but in order to execute programs, the sizes of the registers, the number of registers is not enough. They can be used only for storing temporary data. So they are the fastest storage units, but their size, the size of registers in a computer is very limited. So if its speed is large, its cost is large. Then comes the main memory. So if we cannot store the data and program instructions inside the CPU, then we must have something, a memory, which is out of the CPU and connected to the CPU by the system bus. The size of the main memory is obviously much larger than the sizes of the registers, but as they are out of the chip, access time to main memory is very slow when compared to registers. When we talk about memory, we talk about RAM, random access memory, because we want to write to the memory and also we want to read from the memory. And we specify a memory address and only that memory address can be operated. And there are auxiliary devices like disk, like flash or USB memory, or magnetic tape. Magnetic disk has much larger capacity than the main memory. So we can, if we cannot keep all the programs to be executed in the main memory, we can keep them on the disk and we can move them to the main memory whenever required. USB memory is faster to access than disk, but its capacity is smaller. You know, the size of your USB sticks, and if you compare it to the size of your RAM on your computer, you'll see the difference. And magnetic tape, you can store the data that you want to archive on a magnetic tape because it is very, very slow. So in this pyramid, if you go up, the speed increases, like the registers, the access speed increases, but the capacity decreases. And also the cost of these memory types, if they are fast, they are expensive. The slow ones are cheap. And there's also a cache memory, which I'm going to explain today, is between registers and main memory, because we said that main memory is slow to access, but it has larger size. Registers are very fast to access, but it's not possible to keep everything in the registers. So to decrease the data transfer time between the main memory and the CPU, another type of memory called cache memory is inserted in your computer system. So its size is between registers, larger than registers and smaller than main memory, and it is faster to access than the main memory. Now, let's first talk about the main memory. In many courses, you use main memory actually, like in assembly language programming, you are directly accessing the main memory addresses. Now, let's assume that we have a main memory like this. Each location has a different address. And you remember in Motorola 6800, FFFF memory addresses are available. So when we say a memory address, we talk about a word. Word means addressable memory unit. So if this memory location has an address, it is one word. One word can be 8 bits, 1 byte, or 2 bytes, or 3 bytes. It depends on your architecture. But the definition of a word is the addressable unit. Each word has an address. If you remember our memory from last hour, let me see if I can share it. So I'm sharing the main memory hardware from last hour. I hope the online group can also see it. Here, you remember, there are binary cells. So, and there's a decoder. And we said that the address inputs are like that. This system has 4 words, 1, 2, 3, and 4. And in each word, there are 3 bits. Each word has an address, and a decoder specifies an address. If an address is given here, a 2-bit address, then 4 words can be addressed with that. So therefore, here, each word is 3 bits, but as I said, each word can be 8 bits or 16 bits, 32 bits, maybe, if you want, maybe more. So let's again go back to the previous slide. So therefore, for the memory, there are address lines and data lines. So we can store something through here, or we can read the contents of a memory, and we can specify an address. So this is the block diagram that I'm going to use for main memory. Now we said that cache memory is between main memory and registers. Main memory is out of the chip. It is connected by the bus. Registers are inside the chip. Cache memory is also inside the chip, but it is a larger it is a type of memory, but it's a different type of memory. Now, I want to explain the difference between the main memory and cache by hardware. Both of them are random access memory. But there are two types of random access memory, basically. One of them is dynamic RAM, and the other one is static RAM. Dynamic RAM, DRAM, consists of capacitors. Static RAM, HRAM, consists of flip-flops. So what I already explained is actually that consists of RS flip-flops. It will be called an SRAM. Now, what is specific with the capacitors? Capacitors charge decreases by time. So in order to keep the information without any loss, you have to periodically refresh the capacitors. And that refresh operation takes time. Therefore, dynamic RAM is slower than static RAM. Flip-flops do not require refreshing, so static RAM is faster. What is volatile? Volatile means when you switch off the computer, the values, the data in the cache, in RAM are lost. And when you switch on again, random numbers appear in the memory. So, you know, for example, disks, CDs, your USB sticks, they do not, the information on them are not lost when you take them off the electric, but in RAM, the information is lost. So that's why both dynamic RAM and static RAM are both volatile. And one special thing about capacitors is their sizes are smaller. Therefore, as their sizes of them are smaller, then you can put more units inside a small area. So therefore, the size of a dynamic RAM in the same area, in the same size, the number of units, the number of bits, in other words, the number of cells we can store is larger. So therefore, you can place more cells per unit area. So now let's repeat. The capacitors need to be refreshed periodically, and their sizes are small. Therefore, if a memory that you build using capacitors will have a larger size, but it will be slower. With flip-flops, the memory size is small, but it is faster. Therefore, dynamic RAM is good for large memories. Static RAM is good for small memories. So that is actually what we call cache and main memory. We said that we need a large main memory, but a smaller cache, but a faster one. So the large one can be built with dynamic RAM, small, slow, but large one for main memory. And you can use static RAM for the cache, so that you have a smaller size memory, but faster. So a smaller size memory, but a faster one, can be placed between the CPU and main memory. Okay, any questions about this? Any questions from the online group? Ne gibi? Yani cache mantığı başka yerler, mesela disk cache'i de var. Cache mantığı şeyde kullanılıyor. Yani uzaktan bir detayı getirdiğiniz zaman web üzerinden detayı getirdiğiniz zaman size local bir yerde daha hızlı erişebileceğiniz ve her seferinde uzaktaki yere gitmeniz gerektirmeyecek ama daha küçük size'da, yani Google'ın üstündeki bütün bilgiyi size getirmiyor. Sadece sizin istediğinizi getiriyor. Dolayısıyla hani cache mantığı birçok yerde kullanılıyor. Okay, last hour I explained associative memory. Let's very shortly repeat it. In associative memory, we said that we want to, we have some data in the memory, but we want to do a search operation on that data in a very fast way. So we design a hardware, and that hardware does the search operation on all bits in the memory at the same time. So all bits are searched at the same time, and the result is produced in one clock path. So there was an argument register which we store the data that we want to search. This is inside the memory, associative memory, and the key register checks is used to check which bits should be included in that comparison operation. So the first bit should be compared. So therefore, the first one, it will find it match. Although the other bits do not match, the first 3 bits, because the key register here says that compare only the first 3 bits, the first 3 bits are compared, and it is a match. In the next one, all bits match, so it's a match. In the last one, the rightmost bits match, but the first 3 bits do not match. So as the first 3 bits do not match, it's a miss. It's not a match. So in this way, the match register bits are set automatically in, as I said, in one clock path. And I explained the circuit to design that. Just correct it now. Last hour I couldn't find this sign, so I put a star. Star does not mean last hour's star, does not mean multiplication or AND operation. It means it's exclusive OR. So just correct it now. Online group siz takip edebildiniz mi bilmiyorum geçen hafta ama geçen hafta siz buradaydınız. Değil mi? Yok, salı günü anlattım ben bunu. Online group yine online'dı. Tamam. Şurada star kullanmıştım. Onu lütfen düzeltin. Yani yanlış kalmasın notlarınızda. Bu işareti bulamadığınız için star koymuştum. Şimdi evet, devam ediyoruz. Tabii bunu yükleyeceğim. Geçen haftakini değil. Okay, bunun instruction execution cycle'ı konuşmuştuk daha önce. Ama üzerinden geçelim tekrar. Okay, so we saw now there is a main memory, cache, and associative memory. So usually associative memory is not used like a main memory because it is very expensive to design that circuit for all bits in the main memory. So for one bit, you need to design actually 1, 2, 3, 4, and if you consider inverse, 5 gates to store for each bit, and some more gates for that AND operation. So it is very expensive to design main memory as an associative memory. It would be nice, but it is very expensive. So therefore, Associative memory is usually used for table search operations. Now you will see later that we need to keep some tables by hardware, and those tables, we will keep them in associative memory so that we can search a value in that table in a very fast way. Now, let's consider the instruction execution cycle. In the instruction execution cycle, instructions, first of all, are in the main memory. To execute an instruction, one instruction is fetched from the main memory into the CPU. So this means that to execute an instruction must be read from main memory into the CPU. So that is a memory access. So this is the first memory access in an instruction execution. Then the instruction is decoded, and then the operands must be fetched. We know that the operands are in the main memory also. If in the instruction there is one operand, that operand will be read from main memory into the CPU. That is the second memory access. If there are more operands to read, then the second operand must also be read from the memory. But at least 2 memory operations up to this point. After the instruction execution is done in the CPU. And after the instruction execution, the result must be stored again into the main memory. So that is the third memory access. So at least you need to do 3 memory accesses for an arithmetic operation. But we said that in today's architectures, arithmetic logic units are very fast. There are many components that can operate at the same time, and operations can be done in a very fast way in the arithmetic logic unit. But in order to execute an instruction, you have to do 3 memory accesses. Therefore, memory access time is very dominant in the instruction execution time. And the arithmetic logic units today are designed in a very fast way, in the very fast units, but memories, access speeds are not too fast. So this chart shows the performance increase in memory access time and the processor time. So this line shows the access speed in the memories from 1980s to 2000s. This is the memory performance throughout the years. And this line is the processor performance. And as you see, the processor performance increases much faster than the memory performance. Therefore, there is a gap between them, performance gap. Now, the problem is, and this gap grows 50% per year. So as you see, this is logarithmic axis. So therefore, memory access time limits the performance of your computer. Even if you have the fastest arithmetic logic unit, fastest processor, as you have to access the memory, you cannot get the best performance from that processor. So now our problem is to increase the memory access time. Okay, by hardware, we cannot increase the memory performance than this line. But we can add some more units to increase the performance of memory access. So that is the cache memory, actually. The main memory is out of the chip. It is very, okay, it's not very slow, but it is slow when compared to the others. Compared to the CPU, it is very slow, let's say. So main memory is slow. CPU is very fast. CPU performance and memory performance. So that as I said, cache memory is a faster type of memory made of dynamic RAM, static RAM. So it is faster, but its size cannot be too large. So cache memory is inside the chip. It is faster than, as it is inside the chip, also it is faster to access than main memory, which is out of the chip. And it is made of faster units. But the size of the cache cannot be as large as the size of the main memory. So the system works like this. When the CPU wants to access a memory address, it first checks if it is in the cache or not. If it is already in the cache, it uses it from the cache. If it is not in the cache, it goes to main memory and takes that into the cache and then use it. So it takes it into the cache because the next time it is going to access, it will find it in the cache in that case. And the data transfer between cache memory and CPU is one word, because the CPU wants to access one word, and that word comes from the cache into the CPU. But the data transfer between main memory and the cache is in the form of blocks. Why? Because there is a locality of reference or principle of locality. It means that it's the tendency of a processor to access the same set of memory locations repetitively over a short period of time. So what does that mean? If usually programs are executed sequentially, so if you bring a block from main memory into the cache, a block of data, the next time that you are going to access to the main memory will probably in that block, because instructions are executed sequentially and usually data is accessed sequentially. So probably the next access will be in the same block. So that's why it is brought in like a block from main memory into the cache. So I can give an example like this. You are working in a market and there are no shelves, and one customer comes and asks for what? Bread. And there are no shelves, so you go downstairs, take one bread, and give it to the customer. Another customer comes, one bread, go downstairs, take a bread, give it to the customer. So it's a very time-consuming operation. So you can see it like main memory and CPU data transfer. CPU is the customer asking for the data, and main memory is very slow to access. So instead of that, when the first customer comes, instead of taking one bread from downstairs, if you take a box of breads, let's say 10 breads, assuming that the next customer may want another bread, and put it on a shelf, in that case, for the second customer, okay, for the first customer, you will go downstairs and take the box, so it's the same time. But for the second customer, the bread is already on the shelf, so it is very fast to give it to the customer. So now that box of bread, 10 breads, are your cache. You keep your cache on the shelf, and the next time the CPU is asking for a data, it is already there easily and very fast way. You can give it to the customer, to the CPU. So we have the name hit ratio. Hit ratio means if there are, let's say, 100 accesses to the memory, how many of them are hits? Hit means how many of them could you find in cache ready? And if you increase your hit ratio, you increase the performance of your system. Peki, buraya kadar bir sorunuz var mı? Online grup ve buradaki grup. Ara vermek ister misiniz? Yoksa devam edelim mi? Ne diyorsunuz? Verelim, ara verelim diyor. Online grup, ara veriyoruz.